In this lesson, Unit 5, Lesson 1, we are going to be graphing. So for the first 4 sections, we're going to be graphing, and we're going to be graphing exponential functions. And we want to be able to do that with a function, or with a transformation, without a transformation. We want to be able to write an equation from a graph or a table, and then determine if the exponential function is a growth or decay by a graph or equation. So Chloe, I was not able to record with like my picture showing, but anytime that you need to pause, anytime that you need to rewind, if there's something that doesn't make sense to you, jot down the question and tell me like the timestamp for it. And if you send me that information, like what your question is and what time it happens, then I can help you a little bit more specifically. So, think back to the very beginning of the year, and we talked about different kinds of sequences. We had arithmetic sequences, and we had geometric sequences. And looking at this sequence, which one of those 2 types of sequences is it? This is a geometric sequence. And the reason that we know this is a geometric sequence is because it's multiplying by the same factor. Okay, so 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So you're multiplying by 2 every single time. And so we call 2 the growth factor, or sometimes we can call it the base as well. So what is the growth factor? Well, that's the number that you're multiplying by every single time. So the growth factor here is 2. And we're not going to worry about this recursive function here, or this one right here. But we are going to worry about how to write it in explicit form. So how is the growth factor related to the base of the geometric sequence written in explicit form? The base of the geometric sequence is the growth factor. So if you can find the growth factor, then you've already found the base of the sequence, and that's probably the hard part. Okay, so in this case, our growth factor, or our base, is equal to 2, because that's what we're multiplying every single time. Multiplying by 2 here, multiplying by 2 here. 2 times 2 is 4, multiplying by 2 here. 4 times 2 is 8, multiplying by 2 here. 8 times 2 is 16, and so on. Okay, so what is the form for an exponential function written explicitly? So if it's an explicit function, and again, this is an exponential function written explicitly, this means f of x is equal to a times b to the power of x. A is your y-intercept, and b is your base. Okay, so the explicit equation for this geometric sequence would be f of x is equal to 2 to the power of x. Now, typically when we're talking about an exponential function, this y-intercept is always going to be 1. And so we really don't need to put this on here, because 1 times anything is always itself. So this is what we're going to go with. It's just the base to the power of x. And this is always going to be an x, because the exponent is what's changing. Okay, so like here our exponent would have been 0. This would have been 1, 2, 3, 4, 5, and so on. So if you put 0 in here, this is one thing that you'll want to write down probably. Any number to the power of 0 is equal to 1. Not 0, not the number itself. Any number to the power of 0 is always equal to 1. So 15 to the power of 0 is equal to 1. 397 to the power of 0 is equal to 1. Negative 648.3 to the power of 0 is equal to 1. So anytime that your exponent is 0, your answer is going to be 1. Okay, so we're going to fill out this table really quick. If you need to pause it here so that you can write this table down, that's fine. Okay, and then what we're going to do is we're going to sketch a quick graph. Okay, so I'm going to start here, and then we're going to kind of work our way backwards. So I'm going to start here, fill out these first, and then take these and move it up. So if 0 is our exponent, right, this is our function that we're working with, y equals 2 to the power of x, we would have 2 to the power of 0. And anything to the power of 0 is always 1. Okay, for this one, we would have 2 to the power of 1, which is 2. For this one, we would have 2 to the power of 2, which is 4. And then here we would have 2 to the power of 3, which is 8. So you can see all we're doing is multiplying by 2 every single time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. So if we're going this way and we're multiplying, what's happening when we go this way? So 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1, 1 divided by 2, well, that's a fraction. 1 divided by 2. Okay? You can also think about this as multiplying by a half. So 8 times a half is 4, 4 times 1/2 is 2, 2 times 1/2 is 1, 1 times 1/2 is 1/2. So if we continue to multiply by a half, then this would become 1/4, because 1/2 times 1/2, when you multiply fractions, you just multiply straight across. So 1/4. Okay? Same thing here. 1/4 times a half would be 1 times 1 is 1, and 4 times 2 is 8. So if we are looking at this, you can see that these two are just reciprocals of each other. So I have this right here and this right here. These two numbers are the same, but they're opposite signs. Okay, so we have a positive 1 here and a negative 1 here. Well, 2 to the power of positive 1 is 2. 2 to the power of negative 1 is the reciprocal of 2 to the power of 1. Same thing here. These two are opposites of each other, and their answers are reciprocals of each other. Remember, reciprocal just means you trade the numerator and the denominator. And then same thing here. We've got 2 to the power of positive 3, 2 to the power of negative 3. So here we have 8, and here we have 1/8. So if we were going to graph this, this is what this would look like. So we have negative 3 and 1/8. So negative 3, 1/8 is going to be like way down here. Then we have negative 2 and 1/4. So negative 2, slightly higher. Then we have negative 1 and 1/2. So negative 1, 1/2. And then we have 0, 1. Okay? We have 1, 2, 2, 4, 3, 8. So what this looks like is this sort of line like this. Now, we also have this thing, if you remember back to first semester, we have this thing called an asymptote. Okay, and the asymptote is going to run right alongside that original graph, but it's not, that graph cannot cross or touch that asymptote. So right now, you can kind of see that this starts to flatten out here. It's just going to continue to get closer and closer and closer and closer to this line right here without touching it. So our asymptote, and that word is spelled like this. Okay, so this asymptote is a line that the graph crosses, or sorry, never crosses and never touches. okay? So every exponential function has some things in common. So one of those things that they have in common is that, I'm going to put this, every exponential function okay, so these are functions that are f of x is equal to base to the power of x. So all of these functions have a few things in common. Number one, they all go through the point 0, 1. Okay, they also go through the point 1b. Okay, so what does that mean? Well, whatever this number is here, that's going to be the same as this number here. This is a b, not a 6. Okay, so 1 comma b. That's this one right here. These two are the same thing. Okay, and then the other thing that they have in common is that their asymptote is at y equals 0. So that's this one right here. So every single exponential function has these three things in common. They're going to go through the point 0, 1. So here's the point 0, 1 right here. They're going to go through the point 1, whatever the base is. In this case, our base is 2. And so it's going to go through the point 1, 2. 1, 2. And then the asymptote is at y equals 0. So this is the line y equals 0 right here. Okay, so the next thing that we want to talk about is domain, range, and asymptote. So we probably need to define some vocabulary. So the first one that we want to talk about is domain, and that is all the possible x values. Okay, so when we talk about domain, we're just talking about how far to the left and to the right does this graph stretch. Okay, well, your domain for every exponential function is always going to be negative infinity to positive infinity. And this looks like, we're writing it like an ordered pair, but this is called interval notation. And all it means is that it's going to go from negative infinity all the way to positive infinity. But since infinity isn't a number, we can't include it, and we use these rounded parentheses instead of square brackets. Okay? Our asymptote is at y equals 0. Okay? And the last thing that we want to define is what range is. Range is all the possible, take a guess, y values. Okay? So it's talking about where your graph starts and stops. Okay? From bottom to top. Well, in the bottom you don't see any graph. This graph doesn't cross this asymptote here. Right? It's never going to go below 0. So once we start down here at negative infinity, there's no graph, no graph, no graph until we get to 0. So our range is always going to start at the same number of the asymptote. So 0. And then if the graph is above the x-axis, it's always going to go to positive infinity. And this is common, again, for all exponential functions. Okay, so whatever your asymptote is, and this goes up here for your range. Okay, your domain is always going to be negative infinity to positive infinity. And we would classify this as exponential growth because remember, you read a graph like you read a book from left to right. So as we come over here, this graph is really low, and as we move to the right, it keeps getting higher and higher. It's growing and growing. And so we would classify this as exponential growth. Okay, so similarities of f of x and g of x. Well, again, we talked a little bit about this before. They both have x as an exponent. The difference though is that this one has a base of 2 and this one has a base of 3, but they are both going to go through the point 0, 1. So if we were going to graph g of x, okay, there's a few things that they're going to have in common. So remember, number 1, their asymptote is going to be at y equals 0. So there's the asymptote. They're both going to go through the point 0, 1, and they're both going to go through the point 1 base. So the base here, this is going to go through 0, 1, and 1, 2. This one is going to go through 0, 1, and 1, 3, because the base here is 2, while the base here is 3. So now we're going to go 1, 3. Okay, so these graphs would look very similar, but this one's going to grow a little bit faster than the red graph. Okay, again, domain, still negative infinity to positive infinity. Our asymptote is still at y equals 0, which means that our range is still going to be from 0 to positive infinity. Okay, so remember, x values, y values, asymptote. This is where the graph does not cross. It's kind of like the boundary for that graph. Okay, now, we talked about transformations in the previous unit with just regular equations, but those transformations still apply in this chapter. So initially we had 3 to the power of x, but now we have this 3 to the power of x minus 1 plus 3. So this is the parent function. This is the parent function of this graph right here. So we know that this graph right here is going to have an asymptote at y equals 0. We know that this graph is going to go through the points 0, 1, and 1 base, which in this case is 3. Here's our base. Okay, so it's going to go through 0, 1, and it's going to go through 1, 3. Okay, however, these here tell us that we have some transformations to take care of. So this first one here is telling us, remember, inside the parentheses is your left and right motion, okay? And if it's a negative one here, it's going to change sign. So instead of going to the left one, this is going to go to the right one. But outside the parentheses, we keep the same sign. Remember, outside the parentheses is up and down, and it keeps the same sign. So this one is going to be up 3. So everything that we did here, including our asymptote, is going to shift to the right one and up 3. So start with your asymptote. I always tell everybody to start with the asymptote, okay? So we're going to take this asymptote, this line right here, and we're going to take the whole thing and shift it up 1, 2, 3. So our new asymptote is going to be right here. And we're going to do the same thing with the points, but we really need to do the same of both. If I move this asymptote left or right, you're not going to notice that left and right shift. So really when we talk about asymptotes, we just talk about up and down. But with the points, we need to do both. We need to go right 1 and up 3. So there's the first point, and then right 1 and up 3. And so this graph is going to look something like this. Okay, so this is the parent of this right here. So if we know what this one looks like, we can use it to help us figure out what this one is going to look like. Okay, and again, we have our domain, which is negative infinity to positive infinity. We have our asymptote, which now has shifted up 3. So instead of being at y equals 0, now we're at y equals 3. And remember, the 3 becomes the bottom part of our range. So from 3 to positive infinity is our range. Okay, so let's try graphing this one. So start with the parent graph. We know that the parent graph is going to be 3 to the power of x. So we don't have all of this stuff yet. So this is our parent graph. We know that this parent graph is going to go through 0, 1. We know that it's going to go through one base. Our base is 3 this time. And we know that the asymptote is going to be at y equals 0. So let's just plot these three things right now. Here's our asymptote. Okay, the point 0, 1 is right here. And 1, 3 is right here. Okay, now I'm not going to draw this graph because this is not the graph that we're going to keep, right? This is the parent graph, and we want to graph the transformed graph. So with this, we know that we have some transformations to make. So we have this transformation and we have this transformation. So this one right here, remember inside the parentheses is left and right, and we change signs. So instead of going to the left 2, this means that we're going to the right 2. And outside the parentheses is up and down, so we're going to go up 1. So everything here is going to shift the same thing, right 2 and up 1. So we're going to take our asymptote first. We're going to shift it right 2, and up 1. So our new asymptote is going to be right here. Okay, and I'm going to take away this old asymptote because we don't want this one anymore. We just want the transformed one. So we're going to do the same thing now with each one of these. We're going to move them both right 2 and up 1. So we're going to take this point, right 2, up 1, and we're going to take this point and move it right 2 and up 1. So I'm going to take these 2 points off of here because we don't need them anymore. And now I'm going to draw our new and improved transformed graph. Bada bing, bada boom. Okay, again, domain exactly the same every single time, negative infinity to positive infinity. The asymptote now has been shifted up 1, so it's at y equals 1. And our range is going to be the same thing as the asymptote to positive infinity. Okay, so now we're going to kind of work backwards, and we're going to work from having the graph to writing the equation. So here we have the blue graph is the parent, okay, and the red one is the transformation. Okay, and we can tell this because we know that in the parent graph for any exponential function, this would be our asymptote right here, and it's going to go through the point 0, 1, and 1 base. Okay, so we know that the base for this blue graph is going to be 3, because remember, it's always going to go through 1 base. So the base for the blue graph is 3. So that means that the parent function for this is going to be f of x is equal to 3 to the power of x, right? But what we need to figure out is what is the equation for the transformed graph. Okay, so let's try and figure this out. So if we look at the red graph, we notice that this is where this line starts to flatten out. So this is where our new asymptote is going to be. So this line right here becomes our new asymptote. So that blue asymptote has shifted down 2. So I'm just going to put this off to the side. Down 2. Okay? Now that means that all of these points, in addition to this asymptote, have both been shifted down 2. So what we're going to do is we're going to take this and we're going to go down 1, down 2. But it's not sitting on the red graph, and we want it to be sitting on the red graph. So we need to go either left or right until we hit the red graph. So in this case, we're going to go left, and we have to move 1 unit to get to the red graph. So we shifted this graph down 2 and left 1. So our transformed graph is always going to start with the parent function. Okay, so it's going to start the same exact way. F of x is equal to 3 to the power of x, but we have to put our transformations on this. So remember, left and right goes with the x. Okay, so if we went left 1, that's going to go with the x, but remember, it's going to change sign. So if we went left 1, then this is going to be plus 1. And outside the parentheses, or outside the exponent, down 2, that's your up and down, and it's going to keep the same sign. So if you go down, that's going to be minus 2. So this would be the equation for the red graph. So there are practice problems that go with this, and they are self-checking. I don't know that there are videos with them this time, but they are self-checking, so they'll tell you whether or not you have the correct answer or not. But try the practice problems. The next video is going to be on exponential decay. So a lot of the same things in the next video, just the graph is going to look a tiny bit different.